let's start just by running the user code that I've been working on for a long time. Well, since the last demo, and more time than that, actually. So here's a program. This is sort of the editor mode for the program. As you can see, it's got some UI kind of thing going on with buttons, and it's rendering a 3D mesh and stuff like that. This is not the whole program. There's actually a whole game here, but I don't want to spoil the game. I just want to start by running this to show, like, hey, you know, we're at some point where we're doing some non-trivial things. If you were to put together the feature list of what this program is doing, it's using OpenGL4. You know, obviously it's loading meshes. This is a mesh from a previous game that I worked on, and it's loading textures. You can see the texture map on there. The shader on this is not particularly sophisticated yet, but it is a GLSL shader that can get hot loaded. In fact, we have hot loading on the textures and the models as well. Yeah, and this is an immediate mode GUI system and all that. That's ported over from the Witness editor. Sort of what I'm doing is I'm taking chunks of code from the Witness and pulling them over into the new language as applicable. And the idea being that that does two things. One, it gives the compiler sort of more of a workout, so we can make sure that all these features are really working. And two, it lets me know, you know, whether the language is doing a good enough job, making it easy to implement certain kinds of things, you know, whether there's some features missing or what. I'm kind of warm right now, so hold on a second. I'm going to take off the shirt. All right. That's what I get for double shirting it at the start of the demo. Okay, so this program is around 33,000 lines, and we can get verification of that by compiling it because, well, let's clear the screen. Let's get all this text off the screen. So when I compile it, you'll see, you know, we print out how many total lines were processed, which is 33,000. That includes, you know, all the little modules that we use and stuff, which are not huge, right? The majority of this is in the main program, but so it's a 33,000 line program, including blank lines and comments, which is not the way that I usually count, but it's kind of relevant here if you're going to think about compiler speed the way we are today, because the compiler does have to chew through blank lines and comments along with everything else. Now, the first major thing to say today is that we now have an LLVM backend. As you can see here, we used LLVM to generate the code. This backend was built by Joshua Llvm, who joined a couple months ago, maybe, or I don't remember exactly when, but he's been working on, I don't want to spoil anything else. I'll just say like back-endy and system-y kind of things. And the first thing he did was get LLVM up and running for us. You'll notice that, well, we'll get into this a little bit later, but you'll notice when we compile here, it sort of depends on if the files are warm and in cache or not, but you know, we take somewhere between 2.1 and 2.6 seconds to compile a 33,000 line program, which puts us in the neighborhood of, you know, 10,000 lines per second to 15,000 lines per second, which most people would think that's kind of fast for a compiler. I don't think that's very fast. We'll talk about this again more toward the end. Fortunately, though, most of that time is not our fault, right? So the front end, which is all the stuff that we do, takes 0.22 seconds. And we'll dig into exactly what that comprises a little bit later. And then we hand it off to LLVM, and the rest of this 2.13 seconds. So 1.9 seconds of that is not under our control yet at this time, I would say, right? It's, we'll dig into an illustration of what's happening there. But it's just to say that the front end is pretty good right now, and it's going to get faster. All right, so let me talk for a second about how this backend is enabled. Remember, we had this build options thing. I'll go dig that out for a second. Well, for extra context, for people who haven't seen these before, or for people who have forgotten, you know, what happens is compilation in the system is not controlled by a make file or by external command line arguments, what happens is you sort of boot up a program that's in the same language as the language you're compiling, and that program is, of course, Turing complete and can do whatever you want. And one of the things it does is it configures your compile options with regular code, right? And it sets up a workspace for the target program and instructs it in what files to load and sets the options, right? So in our modules folder, we have this here. So basically, we've got this build options. Let's zoom in on this for a second, right? Where we set overall optimization level, which is more sort of a hint at this point now than anything, because for specific backends, you can go and set options in a much more granular fashion. We have features like array bounds check that we've demoed way back, but down here you can set the backend, right? And this might be a union eventually, but for now, if you set backend LLVM, then these options are relevant, and if you set C, these options are relevant. You still have the option of compiling to C, and we'll show that in a second, right? So for LLVM, you get all these options about what you want to enable, and you can just set those to whatever you want. Most of them are Booleans. There's some other things. There's not a complete list. It's just to give you some idea that you have a good amount of control over what you're telling LLVM to do. For the C backend, we have this thing where you can set a specific compile command. Let me show you how that works. Let me first go and switch to the C backend. So I'm going to comment out this LLVM, and I'm going to put in the C line, right? And that'll just change how we compile. So I'm going to compile here again. And now, we're compiling with the Microsoft compiler. It actually takes less time than LLVM, interestingly. And actually, if things are a little warmer, it even goes just a little bit faster. Now, let me go and I can set this thing that's a callback of sorts, right? So right now, my default, if I have the C backend enabled, is I'm compiling with the Microsoft compiler, cl.exe here. But I also have Clang installed on this system, right? And so I have this routine compile with Clang that I'm going to set. Let me go back here for a second, right? So the only option in C options right now is this, which is a procedure type that you give as a callback, right? And then the system will pass you the name of the C file to compile and the output executable that it should be called, and maybe what the object is called. And then we have a runtime support object that defines a little bit of code, that's like helper code that gets compiled in. And then all the libraries, right? The libraries and array of strings. And we pass you all that stuff, and then you just give it back whatever the command should be, right, as an array of arguments, right? So, so compile with Clang is this, right? I just said, well, so I'm going to make an array called Clang arguments, and we're going to add -w and optimization level 0. I just hard-coded it for that for now. Of course, you could, set a variable that determines that. 64-bit code and blah, 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 whatever. Whatever those options are, add the libraries in, But the point is, this is completely under user control, and of course, you can do anything here that you want. You could go talk to your server and ask it what the build option should be. Now, instead of a callback, this is also a thing that I could have done using the event system that we've demoed before, where you get compile events coming through and it says, oh, it's time to make an executable. And in fact, you could probably piggyback off that even now. But this is a much lighter weight thing where you just give it a little function and you say, I don't want to worry about a whole event loop. It's just that I just want to tell you this one thing of how to compile. So you can essentially use any compiler that you want, right? As long as you can form the command line options, right? So I set compile with Clang. I believe I saved the file. Yeah, so now we're running with C backend and with clang.exe, and that really takes quite a bit longer. Yeah, all right. But that's cool. So that's the bulk of what we've been doing. There's some other stuff that I probably don't want to get too much into, but we've done a lot of work on quality of code generation for the backends, so that so that things like LLVM will be able to do something intelligent with the information that we give them. Okay, so let's talk about compile times, because it's my goal to have things compile very quickly. And here's the thing. Let's go back. Let's turn off client for a second, right? So we're back on the C backend, and we're compiling. And you know that was about 1.9 seconds total, of which still 0.18 is our backend, right? And with LLVM, you know, it's a little longer than that, 2.3 seconds. And here's the thing. We're giving LLVM fully debug options at this time, right? So as far as we can tell, this is the fastest compile that we're able to get out of it. It's possible that there's some things that we haven't figured out or that we don't know about how to feed LLVM that'll make that go faster. But I don't think it's going to ever be orders of magnitude faster, right? I think for a 30,000 line program, we're probably talking on the order of like a second or something at best. Here's the thing. I don't feel like we should really need to wait that long to run a program. Because remember, so this front end time, I'll show you a graph in a second of what exactly this means, but after this 0.22 seconds, so in less than a quarter of a second, we are ready to run the program. We've done all the advanced features like the polymorphism and the operator overloading and everything, and we've actually boiled it down to bytecode that we can run as bytecode, right? So the whole rest of this time, the whole 2 seconds, right, after that is just putting the bytecode into machine code, essentially. Now the thing is that should be, if you were just going to write the minimal thing that you could, that should be a very simple and straightforward task, because there's a one-to-one correspondence between bytecode instructions and machine code instructions, right? If you're not trying to generate the most optimized output code, if you just want something that's going to run, then it should be almost instant. Oh, I forgot to say something. Before we go further into the time issue, let me go back and talk about one other thing. So I'm saying LLVM slow, right? And it is a little slow, but it's really great in the sense that it gives us the capability of generating really high quality optimized output code, which people want, right? I want that, everybody wants that. And a lot of people have put work into code optimization for LLVM, and we are taking advantage of that already. So that's really good. I haven't produced any output code benchmarks yet, but you know, I think they'll be pretty good already. There's you know, when you supply code to LLVM, you know, and for example, how susceptible your language is to aliasing in various ways is going to control what it's able to do with things, right? And then you have a great amount of choice over, you know, what passes you run on things and how. So there's a lot of latitude over tweaking the LLVM output yet, and we haven't done that. So I'm just saying this because people, as soon as you say something like, oh, we've got LLVM going now, people are going to say, oh, I want benchmarks, I want benchmarks. It's like, yeah, we haven't even timed the output code yet. We're not at that point. But we are at the point where I'm pretty sure it's fast enough that I can just ship the initial game that we're going to ship, and it'll be great. Now, the other thing LLVM gives us, it's very important, is a good shortcut to debuggability, right? So over here, I have, this is Microsoft Visual Studio, and I have this game loaded in, and I can just run it, right? Here's what you were seeing a second ago, and hey, I can go to a file and I can set a breakpoint, right? And hey, I can see all the threads, and I can see the call stack over here, and I can browse around. Oh, it gets Visual Studio gets a little confused about output folders a little bit. So sometimes you initially have to tell it that's in the Sokoban folder in editor, and then it'll find it, and then it won't ask you again once it finds it. But you know, so I can browse around the stack. Okay, so we're in main loop. Main loop is calling draw editor view, right, which is calling mesh test, which is calling set shader. Hopefully you guys can read this text on the stream. Let me zoom in a little bit. How do I do that here? Yeah, all right. So this is calling set shader, right, and then that's calling mesh draw, and I've set a breakpoint here in mesh draw, and I can do now all the things from Visual Studio that you would expect, or many of them, right? Syntax highlighting doesn't work. It's disabled because Visual Studio doesn't know this programming language, right? But I'm down here, I can look at my data structures, so I have this texture map. What we did is for every triangle list in this mesh, we look up the material info, we look up the name of the texture map, and then we ask the catalog for the pointer to the texture map. This is not how you want to do it if you want to write fast code, but this was me getting the 3D rendering running, right? So now I have this texture map, I can look down here and I can see, oh, it's 1024 by 1024, and it's got this flag, and it's ID number 48, and whatever, right? Here's the render material, blah, blah, blah. Here's all the color parameters. Just all the value inspection that you like to be able to do from a debugger is good, right? I can step. Here I'm single stepping. We had a little bit of a nonlinearity here where we bounced from this brace back to there, but that's the kind of thing that we're working on. Anyway, here's a rotation matrix that I'm building, right? So I just computed these values, so I can say, what's the cosine theta and the sine of theta and theta, right? And then we make a quaternion here. And of course, I can change values just like in Visual Studio always. So I can change this to like 1, and now I've totally messed up my quaternion. Anyway, so that is great, right? That's a super leap forward. It's super useful. Up until now, I've been debugging things with print statements and whatnot, and you can still do that. But being able to debug with a real debugger is good. And so that's a capability that we have now. Sweet. But, right, as I was saying, there's a downside to that, which is that LLVM is a bit slow. And so what do we do about that? Well, here's what I think. I think in general, there's at least 2 different modes that you're in when you're developing software, possibly 3, but there's at least 2, right? One mode is I want to build the fastest, highest quality shipping code, just like I'm going to deliver it to people, right? And I want to optimize the heck out of that code, right? And I think in that case, you use the Llvm backend. I think the other case, though, is, hey, I want a very fast cycle of compile, edit, debug, right? I want to just change my program, and I want the compiler to just blazingly produce an executable as fast as possible. Well, how fast is reasonable? Well, back here I said, okay, well, our front end time, it tends to be a little bit random here, but it's between 0.18 and 0.22 seconds. We'll call it 0.2 seconds, right? For a 33,000 line program. A program the size of the witness would be 10 times as big as this or more. So we would be talking about 2 seconds, which I don't think is actually fast enough, but I'll show you why we're going to be able to get that faster. So we'll be able to get that a factor of, let's say, 3 or 4 faster than 2 seconds. So if I could compile a game from scratch, full rebuild non-incrementally, like the witness, in 0.5 seconds, I think that's pretty fast. On a machine like the one I'm using right now, this thing that I'm using is a fairly regular desktop machine. I bought it maybe in February or March of this year, and it was a not totally top-end Intel i7, right? So it's not a crazy machine that I'm on right now. It's a machine that many people might have if they're gamers. So I'll go into substantiating why some of these numbers are practical later, but if I can compile in the front end a witness-sized game in 0.5 seconds, right, which also means you could compile some of the biggest game engines in the world in a factor of 10 of that, right? Like large game engines are single-digit millions of lines, right? So 5 seconds to compile something like Unreal or would be much faster than people put up with today with C++. Now that makes some assumptions. You can't necessarily just scale this number linearly to do predictions like that, because things in compilers that go on are nonlinear often, but I don't think they're very nonlinear, and I think there's a lot of optimizations that can be brought to bear. So this is my target number, right? I want to be able to compile large games that I would work on in under 1 second, substantially under 1 second. And the problem is if you start multiplying this LLVM number by 10, it's 20 seconds, 30 seconds, 40 seconds. It gets too big, right? And well, that's all I'm going to say about that. I'm looking over my notes to see. Oh, now, the reason why I'm saying this can be so fast is that almost all legitimate slowness in a compiler is in the optimization step, right? So if you say, I don't care about having the absolute fastest code, right? I just want to get the fastest I can to a running executable, then the compiler doesn't have to do that much work, right? Most work, especially most super linear work, is about optimizing code. Now, usually I think, especially if you're outputting x64 instructions directly, I think you run at a kind of reasonable speed. You'd probably take some speed penalty, like you're twice as slow or something. Maybe a little slower than that, I don't know. I haven't measured, that's a random number pulled out of thin air. Now sometimes what happens is, oh, there's an inner loop that slows me down tremendously if it's not optimized. Well, because we're all one compilation unit, and because we've got this very, very programmatic interface to like how to do things, it would be very easy to add options that say, let's make a non-optimized build, except we're going to optimize this small list of functions because those are our heavy inner loops. And that would still, on the scale of the whole program, that would not take very much time, and yet you'd get the majority of the runtime benefit out of that. So that's sort of a sketch of the plan. Now let me start substantiating all this stuff because you know, I said, oh, we can compile really fast, and some people out there, whoops, I've still got this running. Let's resume the program because that's fun. And where'd it go? Oh, the window's in the background. That's still going. All right. You know, people who have been burned by waiting half an hour for their things to compile or whatever can be understandably skeptical about claims like this, which is why now we're going to go into the fun part of the demo. And we're going to run the telemetry version of the compiler. So telemetry is a profiling system by Rad Game Tools, and I have it here. It is I would say, a professional grade profiler, of which there are only a few that I know of that are really useful, and this is one of them. So I have a version of the game, or the version of the compiler, sorry, compiled with telemetry hooks in it. So when I run the compiler now, it's got hand instrumentation about which procedures I think are important and that I want to time. Now the timing takes a little bit of overhead, so it'll take a little longer for the, whoops. Wait, what are you talking about, Willis?